Hello and welcome back to the lab. So today we're still working on the restoration of the 1946 Packard Pla-Mor Jukebox amplifier. And we're finally coming close to the end here. We're just about ready to finish up. Hopefully by the end of this episode, we will get this thing fully functional and be able to make some tests on it. At least that's the goal. We'll see how it goes. But let's get started. So let's take a quick look at the schematic of the part of the circuit we're going to be working on today. It's a push-pull output stage using a pair of 6L6 pentode tubes. They're actually drawn on my schematic as tetrodes because the suppressor grid, which is internally connected to the cathode, is not shown, but they're actually pentode tubes. They're not tetrode tubes, but I drew them as tetrode just to make it easier. So it's a pair of push-pull 6L6s, like many amplifiers of the 40s, 50s, and 60s use the same configuration. It's a very simple circuit, actually. Takes a balanced input from the intermediate differential amplifier stage that we worked on in the last episode. All right, that's coupled, AC coupled through a pair of 0.047 Mylar capacitors. All the components in this part of the circuit, in fact, most of the components in the amplifier have been replaced with brand new components. So probably everything on this schematic is a new component, with the exception of the power transformer, or the output transformer, of course. Pretty much everything else has been replaced. 0.047s on the input to decouple, to isolate any DC voltage from that's on the input from getting to the grids of the output stage. We have a pair of 330K resistors. In actuality, this 330K resistor is actually a voltage divider to provide negative feedback to the intermediate stage, but I just drew it here as a single resistor. There is a single 330K resistor in this leg. A pair of 100 ohm grid stopper resistors to prevent any parasitic oscillations from occurring in the 6L6 tubes, because they're prone to do that because of their high gain. We have a 240 ohm resistor bypassed with a 47 microfarad capacitor in the cathodes of these 6L6 tubes. This 240 ohm resistor actually in the original circuit was not a resistor at all. It was the coil of a relay that was part of the quick start circuit. And let me explain how that works. In the original amplifier, a relay existed here, and what the relay did was, for the first few seconds of operation, because it's a jukebox, the first few seconds of operation, you want it to actually power up very quickly. So what they did was, for the first few seconds, they boosted the filament voltage of these tubes, in fact, all the tubes, with the exception of the rectifier, from 6.3 volts, which is what they normally function at, they boosted it up to 9.5 volts to heat those tubes up very, very quickly. That was done using this relay that is in the cathode of the output stage. How that works is like this. When the tubes are cold, they do not conduct, so no current will flow through the plates or through the cathodes. That means there will be no current flowing through this, would be the relay coil. The relay is de-energized, and that switches, the contacts of the relay switch in 9.5 volts instead of 6.3 volts to the filaments of the tubes, heating them up very quickly. Once the tubes heat up, they start to conduct, and current flows through the plates and the cathodes of the tube down through the relay coil, energizing the relay, and that will switch off the 9.5 volt filament voltage and switch it back to the normal 6.3 volt filaments that they normally would operate at. So as long as that relay is energized, these tubes will get a 6.3 volt filament. We're not going to use that quick start circuit because I'm not using this amplifier in a jukebox, and I certainly am not going to risk damage to my expensive output tubes by putting 9.5 volts on their filaments. So I removed the relay altogether and I replaced it with the resistor that was equivalent resistance to the relay coil's resistance. It measured 250 ohms. So I replaced it with a 240 ohm resistor. So that's what's in the cathode of this circuit now. So these tubes will take a little bit longer to heat up. That will cause another problem, which we'll get to in a second. But at least I won't be putting 9.5 volts on these filaments or any of the filaments of any of the other tubes in this amp. Okay, the output transformer, its primary is center tapped, and the B plus voltage comes in through the center tap, bypassed to ground with a 10 microfarad 450 volt electrolytic capacitor, and the other side goes to the plates of each of the 6L6s. The output, the secondary of the output transformer, has 4 different taps on it for the 4 different selectable output impedance: 8 ohms, 4 ohms, 2.6 ohms, or 2 ohms. For in the jukebox, you can connect up to 4 external speakers to the jukebox. Put them 4 external 8 ohm speakers in parallel, and you can select the number of speakers using this output switch, which is actually a rotary switch on the top of the chassis of the jukebox amp, and I can show you that in a minute. It's selectable for 1 speaker, 2 speakers, 3 speakers, or 4 speakers. When 4 speakers are in parallel, its output impedance will be 2 ohms, and the effective load impedance of the system will be 2 ohms as well. So there are 4 separate taps on the secondary of the output transformer. We're only going to use 1 speaker. In fact, we're not going to use a speaker at all because I don't have a speaker yet. I had one on order and it hasn't arrived yet. So we're only going to put an 8 ohm dummy load here that I constructed a couple months ago, and I showed you a video on that. So we have an 8 ohm dummy load instead of a speaker. So we're going to set the selector switch to 1 speaker or 8 ohm position. All right. The B plus, the high voltage, comes from the power supply through the field coil of the field coil speaker. Normally, the internal speaker of this jukebox was a field coil speaker, and that means there were actually 4 connections to the speaker. 2 for the voice coil, just like a normal permanent magnet speaker would have, plus 2 additional connections for the field coil, which is a second coil in the speaker that's used as an electromagnet. The high voltage passes through the field coil on its way to the rest of the circuitry, thereby energizing the field coil and turning it into an electromagnet. And the field coil also serves as a filter choke, removing some extra ripple from the B plus power in the power supply. We don't have a field coil speaker, and we're not going to be using a field coil speaker. So the service manual for this amplifier suggests that if you're not using a field coil speaker, that you replace the field coil connection with a 1 kilo ohm resistor. You're supposed to be putting a 1K resistor in this position so that the B plus will pass through the 1K resistor instead of going through the field coil that doesn't exist, right? The service manual doesn't suggest what the power rating of that 1K resistor should be, but we can do a calculation and figure out what that is, and I'll get to that in 1 second. So we have to put a 1K resistor here in this location. I have, in fact, actually put in 2 2.2K ohm 10 watt resistors in parallel in this position for the time being, and I'll actually show you that that is not really going to be sufficient, because the 2 times 10 watts or a 20 watt effective resistor is not strong enough. It's really being overpowered. We need more than a 20 watt resistor. And I can do that calculation, and I'll show you in a second. Anyway, the B plus voltage here passes through into the primary of the output transformer and then on to the plates of both of the tubes. In addition, we have a voltage divider circuit. Divides by, well, it multiplies by 0.8, right? Whatever the voltage is here, we get 0.8 over here at this node. So this voltage goes across another electrolytic capacitor, 22 microfarad, 350 volt capacitor, and it goes to the screen grids of the two output tubes, as well as it also connects to the plate circuit of the previous stages of the tubes. But that's not shown here on this schematic, but it does connect to the screens of the 6L6s. So whatever the voltage is here at this point, we have 80% of that voltage at this point. Okay, so what we have to do is figure out how many volts we're going to be dropping across the field coil speaker in order to determine what the power rating of this resistor has to be. And I do that by doing this. These voltages that are indicated in the rectangles on this schematic are the voltages that the service manual suggests you should be measuring at these points. On the plate, should have 365 volts. On the screen grids, they should have 285 volts. And on the cathode, you should have plus 23 volts. Now, to me, that plus 23 volts seems like way too high a voltage, but that's what the service manual suggests is actually supposed to be there when you measure it. So we'll have to see how that works out. But if you do the calculation, 23 volts across 240 ohms, that's about 100 milliamps, just about 100 milliamps flowing through the two plates and the two cathodes of the two output sections. So we have 100 milliamps flowing through the cathodes, which also means there's 100 milliamps flowing through the output from the B plus into the plates, all right? So if you got 100 milliamps, not even counting the current drawn by the previous stages, we could say it's probably more like 150 milliamps total. If you do the calculation, 150 milliamps across 1K resistor is 225 watts. I squared times R. I squared times R gives you the power consumed by this field coil resistor, right? So it's 22.5 watts if you're drawing 150 milliamps, which is probably what's really going to be drawn through this resistor. I only have a 20 watt resistor here, so a 22.5 watt resistor power dissipation is more than my resistors are rated for. So I placed an order for 3.3K 10 watt resistors that I'm going to put in parallel. So this will really be a equivalent of a 30 watt 1.1K resistor, 3.3Ks in parallel. So those three 10 watt resistors have not come in yet, but I placed the order. They should be here in a few days. In the meantime, I'm going to be using the two 2.2K resistors in parallel, which is only an equivalent of a 20 watt resistor. So it'll be slightly overrated, but we can make some preliminary testing done on this amp to see if it's going to work. I'm sure those resistors will get really hot, but it should work until we can get the more robust 30 watt equivalent resistor to be put in this position. So that's what we're going to do. My concern, I still have another concern besides this concern of the power rating of the field coil resistor, and that is this 450 volt 10 microfarad capacitor is one of those chassis mounted can capacitors that I've already replaced, those Hayseed Hamfest capacitors, those really nice chrome plated can capacitors. it's only rated at 450 volts, which is supposed to be rated at. That's what the original was supposed to be rated at. The problem arises, the rectifier tube is a directly heated cathode rectifier. So that rectifier heats up very quickly and provides B plus voltage here very quickly. These cathodes are indirectly heated with a 6.3 volt filament. They're going to take longer to heat up now that we've removed the quick start function from this amplifier. They're going to take longer than 1 or 2 seconds to warm up. And until they do not draw any current. So if there's no current being drawn through the B plus line, there's no voltage drop across the field coil resistor until the tubes warm up and start drawing current. When there's no voltage drop across this field coil resistor, whatever voltage you have here at the B plus line is going to appear all the way through here onto the 10 microfarad 450 volt capacitor. Now with no load, what we were measuring here at the B plus line, 587 volts, which is way more than 450 volts. Now I can tell you that I've already tested out this circuit, and it does seem to be work. It doesn't blow up. There are no explosions, right? But we are really overstressing this capacitor at the start of power up because there's no current flowing through the output tubes, and yet there is the full B plus voltage applied to here. There's more than 150 volts, or more than 100 volts more than this rated capacitor. Now it seems to handle it okay for the short time being. Once you start drawing current, of course, that voltage drops significantly and becomes way below 450 volts, and the capacitor is fine. But at the very start, the capacitor is over voltaged by probably something like 100 volts too high. I have ordered some replacement electrolytics to put in here, and we may come up with a circuit to try to remedy that situation further. But for the time being, it seems to work, so I'm going to go ahead and leave it there for the preliminary test at least. I ordered those capacitors at the same time I ordered the higher power field coil replacement resistors. So those should come in at the same time in a couple of days. But for today, we're going to try to run it with 20 watt resistor here and a 450 volt capacitor here in this position. All right, so let's take a look underneath the circuit and see what the wiring I have done. Okay, time for the quick safety warning. The kind of voltages we're talking about in a circuit such as this, 400 volts, 500 volts, those are lethal voltages. If you don't know what you're doing, please refer servicing to a qualified person who does know how to work with this type of circuitry, because you don't want this to be the very last amplifier you ever get to work on. Okay? All right. So we're looking at the underside of the chassis now. Let's see. Here are the two output tubes, the 6L6 tubes. These two capacitors, one here and one underneath over here. Those are the two inputs capacitors that come from the differential amplifier of the previous stage. Those are the two balanced input caps that isolate the plate voltage from this tube into the grid voltage of this tube. The grid should be at 0 volts. All right, we have the 330K resistors over here that go to ground. Let's see. Here's our output transformer, and the center tap of the output transformer is this wire right here, and the two other sides of the output transformer connect to the two plates of the two tubes. All right, this is that 450 volt capacitor that I'm afraid may be over voltaged when at first power up here. It's wired in place, but we may have to do something different with that capacitor. I'm not exactly sure. I know that I've tried it very briefly, and it seems to handle it okay. There were no explosions or anything like that. So here is the power resistor that I'm using to replace the field coil. Currently, it's a pair of 2.2K 10-watt resistors in parallel. So it's the equivalent of a 1.1K resistor, or 20 watts. It gets very, very hot because there's really more than 20 watts being dissipated through these pair of resistors right now. We're going to replace that with 3 10-watt resistors to make a 30-watt resistor as soon as those resistors come in from the mail order supplier. That should be in a couple of days. The B plus comes in over here, goes through the voltage divider, which is this pair of resistors mounted on the side, and that voltage goes to the screen grids of the 2 tubes, as well as the plates of the other stages of the amplifier. This 4-terminal socket is the output speaker connector that connects to the output of the voice coil and the field coil. If you use a field coil, you can see that the field coil connections are not connected at all. I didn't want to put 450 volts on the socket on the top of this chassis, so that's why those field coil connections are not connected any longer. The output of this speaker jack is also connected to the screw terminal output jack, which is over here, and the output impedance selector switch, which is this rotary switch here, which is on the top side of the chassis underneath. All right, so that's the output circuit. It's completely wired up and ready to go. So I guess there's nothing left to do but to turn it on, make some measurements, and see if the voltages are appropriate, and then we'll try to see if maybe it actually amplifies a signal. Okay, so I've hooked up 3 voltmeters with the 3 red probes. All of the negatives on my voltmeters are connected to the ground wire. Okay, all the black terminals are connected to the ground wire. This voltmeter measures the cathodes of the 6L6 tubes. The manual says 23 volts should appear at that point. I'm a little skeptical of that. That seems awfully high to me, but we'll have to see. We also have measured the input side of the field coil speaker and the output side of the field, not the speaker, the field coil resistor, and the output side of the field coil resistor, so we can measure the difference between those 2 voltages to calculate the amount of voltage drop across that resistor, and in fact the amount of power dissipated through that resistor. This output voltage is the voltage that appears on that 450 volt cap that we're concerned may be over voltage stressed. So we want to keep an eye on that voltage as well. When I first turn it on, that voltage will probably be far more than 450 volts, but it seems to handle it okay for that short period of time until the tubes start conducting, and then the voltage drops. So we'll make some measurements of that. We'll take a look at that. Let me focus the camera on my 3 voltmeters, and we'll plug this thing in and very carefully turn it on, and quickly turn it on, I should say. I don't want to blow anything up, but we're going to do it. Oh, I should also mention that we have connected my 8 ohm dummy load in lieu of a speaker through this wire to the screw terminals that are the output speaker connection terminals, and the output impedance selector switch here is set to 8 ohms, which matches the dummy load input impedance of 8 ohms. So this will be instead of a speaker. Okay, so here are my 3 voltages. At the top we have the highest B plus voltage. That is at the input to the field coil resistor. In the middle we have the output of the field coil resistor. This is the voltage that we don't really want to go above 450 volts, but appears that it probably will do so at least initially, until the tubes start conducting and drawing current, and we can drop down below 450. So we'll have to watch that. At the bottom is the cathode voltage for the 6L6 tubes. The service manual says that this voltage should be plus 23 volts. I don't really know how that will work out. That seems like too high to me, but I'm not sure. But that's what the service manual says should be the correct voltage there. So we'll watch for 23 volts. We want this to be less than 450, and we really want the difference between these two voltages to be less than about 140 or 150 volts. If it's more than that, we're going to be overstressing that field coil resistor. We actually have solutions to both of those, but they're on order and those parts haven't come in yet. So let's turn it on. It's plugged in and ready to go. Hopefully no magic smoke will be released. Ready? Here goes. Let's keep a close eye on this this voltage. 489 volts, 490 volts. And now it's dropping down below 450, which is what it needs to be. Give them a second to stabilize a little bit. Looks like we're at 348 volts. That's pretty good. The difference between this one and this one is more than 150 volts. So we're putting more than 20 watts. We're dissipating more than 20 watts through that field coil resistor. So it's probably getting pretty hot. 19.2 volts on the cathode, not really 23, but that seems a little bit more reasonable, but I guess everything is working. All right, looks like our amplifier may be working, but does it amplify? Let's find out. All right, I turned everything off and unplugged it and monitored the voltages to make sure they've discharged down to a safe level. I wanted to just kind of see how hot these resistors are getting. It's quite warm. It's quite warm still. It's been off for about 30 seconds, I guess. And it's still very warm to the touch. It's being these power resistors are being overheated. So we have replacements. Get an extra 10 watts of headroom there in the power dissipation rating for these resistors. When those come in, I'll swap them out. That should work out just fine. I think the 1K, the 1.1K we're using here is a good value for that resistance. Originally, we were using 4K before we had the output stage connected. And the 4K would seem to be working as well. But with the output stage connected, we're drawing a lot more current. And 1K seems to do the trick. All right, so let me hook it up to a signal source. And we've already got the output dummy load, 8-ohm dummy load connected to the output in lieu of a speaker. So let me take the output of that and hook it up to my scope. And we'll put a signal on the input, and we'll compare the input to the output, and we'll see if we're actually amplifying. Okay, so here's the setup. The amplifier is still upside down, of course, in its little wooden frame. We're going to take that off as soon as we make sure that it's working and stuff. But right now, we have connected to the phono input. We have my 200 CD oscillator. Okay, the output of the speaker output of the amplifier goes to my 8-ohm dummy load over here, and the output of the 8-ohm dummy load goes to my channel B of my scope. So channel A is looking at the input, and we have the 200 CD set for 2.8 volts peak to peak, which is 1 volt RMS. So channel A is looking at the input signal over here. Channel B will be looking at the output signal. Now, I did a little calculation and found that about 8 volts peak to peak will be equivalent to 1 watt across 8 ohms. And about 25 volts peak to peak will be the equivalent of 10 watts across 8 ohms. So we'll have to see if this thing can put out 10 watts. According to the specifications, it puts out 16 watts. So let's see if it amplifies at all. We'll see if it can put out 1 watt, and then see if it'll put out 10 watts. And here we go, ready to turn it on. I don't want to leave it on for very long because those components are still stressed a little bit until I can get the replacements of the higher voltage rating for these components. But here comes the signal. We do have an output. All right, right now we're looking at 2 volts per division, and we have an output signal of approximately, what is that, about 5 volts peak to peak. Let's dial it up a tiny bit more. If we can get 8 volts peak to peak, that would be 1 watt. There's 8 volts peak to peak. That would be 1 watt of output. The volume control is set to just over 2. Wow. Okay, let's see if we can get 25 volts peak to peak. That would be 5 volts per division. That would be 5 full major divisions. Wow, it's working. Wow, it certainly is working. It's putting out more than that. Okay, there's five full divisions. That's 10 watts on the output. See if we can dial it up a little higher. Oh, we can. It starts to get distortion. You can actually hear, I don't know if you can hear in the video, but I can hear the tubes of the transformer or something actually singing. I can hear the 1 kilohertz tone coming out of something in this amplifier. It works. It puts out more than 10 watts for sure. All right, I'm going to turn it off because I don't want this thing to get cooked. So I'm going to turn it off, but it does work. All right, well, I don't think I want to press my luck anymore. Let's turn this thing off. And let's wait for those new replacement parts to come in for the higher wattage power resistor and the higher voltage rating of that capacitor. And we'll get those parts installed. We'll do some more complete, thorough testing of this amp with some vintage test equipment, as well as maybe some more modern techniques. And we'll get the bottom plate put onto it and take that goofy wooden frame off of it, and we'll have a completed amplifier. I'm real excited, though. All right, thanks very much for watching. Please like and subscribe. And stay tuned as we do the final episode of the 1946 Packard Pla-Mor Jukebox amplifier. Thanks again.